Hey everyone, I'm Mitchell and today I'll be talking to you about a case study of a GIS model for steep slope risk management. A bit of a context, shouldn't be a surprise to everyone that we have a problem with steep slopes in New Zealand forestry. We all understand the damage that can occur from debris flows, but at the moment we don't have a single unified approach on how to manage them. It's mostly companies developing their own methods. So we've got a number of tools in New Zealand that have been developed, and today I'll be talking about one of them developed by a company in the East Coast region. So the tool's called the Catchment Risk Matrix. It serves as an exemplary case study illustrating the potential for effective risk management and measurement in New Zealand's forestry sector. The model's been designed to offer valuable insights into steep slope risk, aiding forest managers in making decisions and operating restrictions. A sensitivity analysis of the catchment risk matrix has been conducted. This delves into the tool's various parameters and variables, giving a clearer understanding of how they influence the risk assessment. By examining the sensitivity of these factors, users can make more informed decisions regarding forestry operations, land management, and mitigation strategies. This ensures that forest stakeholders can take proactive measures to reduce the risk of debris flows in vulnerable areas. So I used a localized approach looking at 3 sites across the Gisborne region to cater it towards specific geographic and topographic characteristics of the area. So this is the user interface of the model. So up the top, you've got your input digital elevation model and your flow accumulation threshold here. I'll get into that in a bit, and then an output where you save it, and then you click go and it runs it. So it's a fully automated process pretty much. So how the model works, so you put those 2 inputs in, creates a map of the catchments, and then for each of those catchments, it calculates these variables here, the percentage of catchment over 35 degrees, the size of the catchment, and the ESC class of the catchment. And then based on those variables, it assigns each catchment a risk. So just going back to that flow accumulation threshold, that basically is what level of flow accumulation is classified as a stream. So if you've got a lower flow accumulation threshold, you're mapping more streams. If you've got a higher one, you're mapping less streams. And then this stream network is what is used to create your map of catchments. So if you've got a higher flow accumulation threshold, you're mapping in less catchments. If you've got a lower one, then you can see you've got a lot more. Like for example, this one here is being split up into about 4 or 5 on that side. And then the DEM resolution is the cell size of your elevation model. So when we changed that flow accumulation threshold, I found that the main risk code that was influenced was the hazard code. So that's from the ESC class, and that's shown up in that graph in the top right. You can see as the flow accumulation threshold is increasing, it's going from a risk of 4 down to a risk of 2. So that's basically your catchment's getting bigger, and then within that catchment, there's multiple ESC classes. So there's a bit of an error there. And then at site B, I noted that there was some decrease in the slope code when the FAT was over about 2 million. And at that point, there was only 2 catchments being mapped. So the time taken for the model to run varied quite substantially when the cell size was less than 5 meters. So you can see when you've got a 1 meter DEM taken up over 2 hours. I can tell you from first-hand experience, that's pretty punishing when you're doing that on a consistent basis. So managers might think about shifting to a lower resolution DEM and trying to get it out a bit quicker. Then that has this sort of effect here. You can see as you're reducing your DEM resolution, we're getting a lot more area moving down a slope code. So in this diagram, it's mostly in 2. That's with a 1 meter DEM input. And then with the 25 meter DEM input, it's almost entirely moved to 1. The area code and the hazard code were not influenced substantially by the DEM resolution. So this graphic here is sort of changing the input DEM resolution and showing how the slope over 35 degrees changes with that. And then this graph here is showing the same sort of idea with a 1 meter DEM at site C. We've got 27% over 35 degrees. And then when you're at the 25 meters, you got just over about 15%, 12%, sorry. So just to summarize, I've looked at 3 sites in the Gisborne region, conducted a bit of a case study showing what is possible so that other companies have an idea of how they can manage their risk. The model was easy to use and acted predictably for my sensitivity analysis. I was able to visualize and quantify risk throughout areas, but there are some opportunities in the future to develop this model further. That could be incorporating downstream risks or other factors such as rainfall, preparatory factors, or if you know the history of the area and there was previous failures, could incorporate that. And the accuracy of this model has also not been assessed. Thank you for your time.